All right, colligative properties. So those colligative properties, what is it that they do? Okay, so they're just simply going to affect the boiling point and the freezing point. So we've got, yeah. So we'll call it freezing point depression. So anytime you put any kind of solute into a pure liquid, its freezing point is just going to drop. And then what happens to the boiling point? Goes up. Okay. So no matter what happens, if you put a solute into a pure liquid, its boiling point goes up. It doesn't necessarily need to be a salt. It's just that salts are most effective. So the same thing will happen to sugar water. Sugar water will boil at a higher temperature and freeze at a lower temperature than it will regular old water. And so how does that affect the liquid state? It really just so it's liquid over a longer period or a longer temperature range. Okay, so we throw salt in, and why does the boiling point go up? The first thing we should be thinking about with this is, what does boiling actually mean? That molecules will be breaking intermolecular forces, right? So tell me why the boiling point's going to go up. Not that there are more molecules, that's a good guess though, but not that there's more. By throwing the salt in, you've changed the intermolecular forces for something like a hydrogen bond into something like a dipole ion. So what we had before was, when we're just simply talking about a water molecule, right? I have a water molecule, and this water molecule is going to try and boil away, right? And then there's another water molecule that's still in the liquid state, and under normal circumstances, you need the amount of kinetic energy. So that redness right there, that's the intermolecular, oh, you can't really see that on the page. The intermolecular force happening between the two water molecules. And that is a hydrogen bond because the O and the H have partial positives and partial negatives. But then if I switch this to a sodium ion, that charge is a full +1 charge. And so it's going to be a lot more difficult for this oxygen to break free of this sodium than it will be to be able to break free of another water molecule. So really the intermolecular forces had switched over from one intermolecular force to a stronger intermolecular force. So you literally need more speed, and speed is kinetic energy, and kinetic energy is measured by temp. So as long as I get that water molecule moving fast enough, it can break free of the sodium as well. It's just going to need to move faster than it was to break free of regular water molecules. Okay, and the freezing point depression, how about that one? No, it's really the same sort of thing where the molecules reorient themselves because of the stronger intermolecular forces. It's an intermolecular force change. And the issue in this case is the water molecules, you know, I should actually draw it the way it looks. The water molecules are organized in nice hexagon shapes, interlocking hexagon shapes, being attracted to each other. So you'll get this attraction force between these water molecules. And the attraction force is an intermolecular force thing. They're doing that because there's a partial positive and a partial negative. And so that's why they're attracted to each other. And if I go and I drop a sodium ion in the middle here, what are all the oxygens going to do now? They're going to turn to it. So here what I have are, in this little intermolecular force here, I've got oxygens being attracted to hydrogens, and they're both partial positive and partial negative. But this here is a full +1 charge. That oxygen is going to be like, okay, there's a partial positive H there, and there's a full +1 Na right there. I'm going to reorient myself to the Na. So what ends up happening is so I have a nice organized structure, basically interlocking hexagons, and that you get that snowflake shape. And then when I drop a sodium in there, the snowflake shape gets all messed up because they are not in line with each other. And all I need to do to have a liquid is to break up a crystal matrix structure. So let's say you had a huge Lego structure or a huge Lincoln log structure, and then somebody came in and started pulling Legos out. What would the structure do? It'd fall apart, right? If the Legos couldn't lock up with each other, the structure would just fall apart. And so that's what's happening here. The solid is a structure. And then when I break up that structure, then the water molecules fall apart, and now they're back into the liquid state. Calculate the final concentration. Okay, so this is actually not a very hard question. It's just kind of confusing to think about for a sec. So what are we trying to calculate here? Concentration, right? So we're looking for moles per liter. So what I need is moles and I need liters. So if I can put the total number of moles divided by the total number of liters, I'm done. So do we know what the total ending volume of the solution is going to be? So let's just add those guys up. So I've got 2 liters, I've got 0.4 liters, and I've got 0.25 liters. So 650, so 265 liters. There's my total volume, right? Okay, so now I need to figure out how many moles I have. So in the 2 liters, there's 0 moles of solute, so I don't have to worry about that one. And I just need to calculate how much is in the 250 and the 400 milliliters. So since I'm just looking for moles, I'm going to write 1.3 moles per liter, and I'll write 0.25 liters, and then the moles will or the liters will cancel, and then I've got 1.75 moles per liter, and then that was 0.4 liters, so the liters cancel out there. All right, so let's calculate that. I've got 0.25 times 1.3, and I've got 1.75 times 0.4. So I've got 0.7 mole, and I've got 0.325 mole. So these are the total number of moles that are going to be in this container now, because now they're both in the same container. So I'll just add these guys up. So I'll get 1.025 moles, and I'm almost done. So I take my total number of moles that I know that are in here, I divide it by my total volume, and I'm going to get a molarity. Okay, so 1.025 divided by 2.65, and I get 0.39 moles per liter. I think sometimes with problems like this, it's easier if I take some containers and I think about dumping them into a container. So there's a certain amount of moles in this one and a certain amount of moles in this one, and there's no moles in this one. So we're just trying to figure out how many moles in total liters I've got. Say again?
Instead of 0.39, I got 0.13.
Oh, let's see if I punched that in wrong. No. No, it should be not too far from half, right? Because it's 1 divided by 2.5-ish. All right. How about this next one? Can you?
The one we just did, where'd you get the 0.25?
250 milliliters.
Oh, okay.
Just move the decimal place over 3 spots. All right, so how about this next one? Which one of these is a better electrolyte? So the first thing we need to ask is what's an electrolyte? And for an electrolyte, I've got to have water, and then I've got to have something go into the water and break up into ions. So we need to make sure that both of those things break up into ions. Is calcium chloride soluble? It is, because the chlorides are soluble. How about the magnesium sulfate? Yeah, because of sulfate. So both of those things are going to break up into, so they'll both be, make the solution electrolytic. So now, is there one of them that's going to be better than the other? When this one goes into the water, it's going to break up into how many pieces? 3. There's going to be a calcium plus 2 and 2 chlorides minus 1. And then what's this guy going to break up into, the magnesium sulfate? Nope. It's going to be, it's going to be a magnesium with a plus 2 charge, and it's going to be a sulfate with a minus 2 charge. That sulfate's not going to break up into its pieces because it's a polyatomic ion. So only 2. So if you had a bunch of ice on your driveway, which one of these 2 things would you want to throw down? The calcium chloride for sure. It'd be 50% better functioning than the magnesium sulfate. Although you might have magnesium sulfate at your house, you probably don't have a lot of calcium chloride. Do you guys know what the magnesium sulfate's common name is? Epsom salt. You might have that in the medicine cabinet in case you have a injury or something like that. Epsom salt in a bathtub if you're really sore, really good. Really good. Okay, so what's the percent solution? Grams and 400 milliliters. All right, so straightforward. So 35 grams and 400 milliliters of solution times 100. And so I'm going to get 35 divided by 400 times 100. I get 8.75% and mass volume. This should be written next to the calculation, because what we did is we took a mass and divided it by a volume. And so the person might want to know if it was done mass to mass or volume to volume, or in this case, mass to volume. What is the volume of alcohol in a 454 milliliter beer with 3.5% alcohol? Okay, so in this case, we already know that it's 3.5%. And it's got to be multiplied by 100, and I've got 454 for the total volume, and I don't know the volume up top. So my volume up top is going to be equal to 3.5 times 454 milliliters divided by 100. And so 3.5 times 454 divided by 100. 15.89, so like 16%. Sorry, 16 milliliters, not percent. Does anybody know what beer that is? Really low alcohol concentration. Like Budweiser is almost 6. It's Guinness. Guinness has a low alcohol concentration. Which equations did I use for the previous one? So for this one, I used mass to volume percent for the first one, and for the second one, I used volume to volume percent. Okay. What is the Fahrenheit freezing temp? Okay, so that makes this one a little more tricky. So I've got the change in the temperature of the freezing is equal to NmKf, and I've got magnesium chloride, and what's the N value in this problem? How do I get that?
So that's the number of moles?
Yeah. Per molecule. So how many pieces does magnesium chloride break up into? 3. Magnesium plus 2, and then the chloride 2 negatives. So then for this problem, my N is going to be 3, and then 2.5 is my moles per liter. And then my KF is going to be 1.86 degrees C. Liters and moles, so those all cancel out. And so what do I get here? 1.5 times 1.86. How if I put times 1.86? Wow. 8, 6. 13.9. Sorry. 13.95 degrees C. But I asked about the Fahrenheit temp. So let's think about what is this here? What did we just calculate? Say that again? How much it what? Increased? What's happening here? What are we talking about? So what's the freezing point do when I add salt to it? First question on this homework. I put salt in, what happens to the freezing? It depresses it, right? So what's the freezing point in degrees Celsius now for this water? Yep. So this is a change in the freezing point, right? And the change, that delta, is temperature final minus temperature initial. And in this case, my temperature is equal to the change in temperature. And so what I know is my change in temp is 13.95 degrees C. I don't know my temperature final, but I do know my temperature initial, which is, in this case, 0. So if I rearrange this equation, I got to put the negative sign over, right? And so I end up with my final temperature being negative 13.95. Great. So now that I know what that temperature is, and then I just need to do a conversion from Fahrenheit, or from Celsius into Fahrenheit. So my temperature Fahrenheit is equal to negative 13.95, and it's times 9/5 plus 32, or did I get that backwards? Let's find out. So negative answer times 9 divided by 5 plus 32. No, that looks good. 6.89 degrees Fahrenheit. What if you forgot the negative sign? What would our answer look like? It'd be significantly higher, right? And you should be thinking about that, because it's got to be freezing point depression and boiling point elevation. So does this number make sense for Fahrenheit? Yeah, it freezes at 32, and this is saying it freezes at a lot colder temperature. And if it came back and said that it now froze at 62 degrees Fahrenheit, you should be thinking, all right, I made a mistake someplace in there, because that doesn't make any sense. It always makes the liquid state get bigger. Okay.